I'm going to try to summarize exponents and logs for you. Now, let's just say the story is you have 10 of something, you're doubling repeatedly, and you want to know how long will it take for me to have 300 of that particular thing. Now, to do that, you could plug in numbers repeatedly, all right, to this. Plug in 1, plug in 2, plug in 3, and sooner or later you get close to 300. It's probably going to be a decimal, not exactly. So you could do that. And when you plug in numbers, what you're really doing are graphing. You're finding dots for a graph, then you sketch the graph, and you have a story in a graph. You can also have a story as an equation. We're making a story out of it. So, now, with that said, how would you solve this? How would you find out how many times to get to 300? Well, let's see our normal way of solving. What we would do is we would divide both sides by 10. This is our normal way. Then we have 2 to the what power equals 30. All right, now you stop and go, okay, wait, I can't figure this out. Because when I power 2 over and over, I'll never get 30 as an answer. So I'm stuck with a decimal. So we have to create another way to solve this. And what they did is they made something called a logarithm. And what we did is we wrote this particular equation as log base 2 of 30 equals x. This statement is the same as this. It's just another way of writing it. All right? Because now I have x equals something. Now, once we did this, we changed this into this logarithm notation. Now we have to make a whole new story about logarithms. They opened up a whole can of ideas. So this right here has a value. It's actually a decimal. And we can learn how to solve this and all the properties related to it. And we have now found how to find problems when x does not work out nicely, when we can't just look at it. Again, we could have made a graph in the beginning to see when it equals 300. Could have made a table of values and approximated, but we need better ways. And so we're using solving methods. All right? So now, how and what does this mean? Well, it means 2 to the what power is 30. How do you find the value for this? Well, you use a calculator. It's in your calculator. There's a way of doing it. There's like one of the properties we end up using is this. They go, okay, they'll say x is equal to, this is log 30 over log 2. Now, wait, what did I just do? Well, what happened is we broke it into 2 different logs, and you can put these in your calculators, and you can find the value of this and find out what it equals. There's also some other properties you can do with logs. I mean, it goes on forever, because just like exponents have properties, so do logs. For instance, you could have wrote log base 2 as log 3, let me go back a little bit, 3 times 10 to get 30 inside, which that would, in log terms, you can make that log base 2, 3 plus log base 2, 10. I mean, there are so many things. So you could actually make 30 into a 3 times 2. That 3 times 2 can be separated as 2 different logs with a plus between. It's just a property of logs that comes up, and you learn about that. It's called expanding. You can expand it into that. Why would I want to expand this to look like this? I don't know, but it has a property, and there's sometimes where it is important. So we have a basic idea here, which leads to something called a logarithm, which leads to properties of logarithms. Man, all this leads one thing to another. Now, once we learn about logarithms, well, can't we now graph logarithms? And graphing, all graphing is saying plugging in numbers. For instance, I could have just found what's f of 2. F of 2 equals 3 times log base 5 of 2 plus 4 minus 2, and I can calculate this if I know how to calculate it. I can then plug numbers over and over into this, then I can make a graph of it just by plugging numbers in over and over and over. But what we learn in math is we tend to learn shortcuts on how to graph these. We learn key ideas that help us out. And what we learned for graphing this, other than plugging numbers in over and over again, is we learned, hey, this right here helps us find nice, clean numbers to plug in. So we said, what plus 4? Well, we want it to equal 1 in the base. Basically, we want this to equal to the base or multiples of the base. So the easiest multiple of 5 is 1. We also, well, let's just make it equal to 5. You could have also done 25, any multiple of 5. But we find is these two are easier. And when we solve those, what we notice is we minus 4 over, we get x equals negative 3. We minus 4 over, we get x equals negative 1. What does that matter? Well, if I were to plug in values, f of negative 3, f of negative 1, if I crunch those using this, I'll get nice, clean results. And those clean results help us make graphs. So, from those dots, we get a graph. We could keep putting dot after dot after dot. We could put this one. We could even put decimals because your calculator could crunch them. But these are nice outputs, and we make graphs. Now, the weird thing about logs, they also have issues. You cannot do logs with negatives in the inside because there's this asymptote thing. And so what you also have to realize is that x plus 4 cannot equal 0. When you do that, what you run into is you minus 4, and what you get here is x cannot equal negative 4. Actually, x has to be larger than negative 4. This is something you're going to run into with logs because anything where you get less than negative 4, which creates the inside being negative or 0, has errors if you try to plug them in. And so there's this asymptote. And so what you end up with is a real quick sketch is this asymptote at x equals negative 4. And then you get these two values, whatever they pop out to be, end up looking like a graph like this. And you get a dot here somewhere and a dot here somewhere, and you get a sketch whenever you plug those in. And this is a logarithm graph. And we learn how to make find good values, plug them in, and find exactly what it looks like. But this is one idea. Next, what we do is we talk more about exponents. And when we look at exponents, we go, hey, this is a story, really. Let's talk about the story behind this exponent. What this story is saying is I have let's say $3, and I am growing by a rate. Well, what's my rate? I'm growing by a rate of 7%. Where do you get that from? Well, if you multiply by 1, it's going to not change. But if you multiply by something bigger than 1, it's going to grow. So how far from 1 is it? It's 7 cents. So that's a 7% growth repeatedly. And my story wants to know when I'll have more than 200. So if I solve this, I will find out when $3 at 7% growth repeatedly will be bigger than $200. And that is a story you can solve. You can solve using mechanisms of solving, which you also learn how to solve these things. And one way you could solve it is you'd use your method of, well, divide by 3. So I got 1.07 to the x is greater than or equal to 200 divided by 3. Then you change this to a log, and you get log base 1.07 of 200 over 3. All right, you flip the inequality. There's something behind that because you're moving the x to the other side. And what happens here is if I put this in my calculator in some fashion, I can actually find out how how long it will take for this $3 at 7% to become $200. And I want it's going to be something over that because I want bigger than or equal to. But that you can solve that. Okay, here's another story. I have $500, and if you multiply by something smaller than 1, you're going to shrink it. Okay, so let's say I have $500, and I'm going down by how far down is that? Well, that's 13%, because I'm dropping by 13 cents. So it's 13% droppage, and I want to know how long would it take for me to have under $100. Well, again, I can use this process. I can solve it and find out how long it would take, how many times I would have to take 13% to get below 100. And then we went into even more. We talked about this E. What is E? E is a naturally occurring base in logs. It actually has its own base. It's called ln. Log base E is ln. It's a whole other story. And this is a whole other story. This is called Newton's law of cooling. Newton's law of cooling talks about that it's a natural decaying temperatures. And this is a 5% droppage. So Newton's law of cooling talks about this is a 5% decay of cooling. Okay? This is also interesting. You have right here an 80-degree room. And your initial temperature would have been, well, if we take this whole thing, we plug in 0, it'd be 200 plus 80 would equal 280 degrees is my initial temperature before I took it out of whatever oven or whatever heating up it was. And this is the room temperature, so it will never shrink below the room temperature at 5% repeatedly. And this is just a story. It's a story because we start with plugging 0 in, finding the initial temperature. We then shrink at a certain rate. And our story wants to know, when is this going to be less than or equal to 100 degrees? Because we don't want to burn ourselves. How long would that take? Well, we can solve this. We can use this method we talked about up here, and we can solve it. And that's why we solve. Why do we have solving? So we can answer questions that relate to life. And exponents are very life. It's very exponential. And why do we have logs? Logs are used to solve exponents. Once we've made logs, we then need to learn how to deal with them and the properties they have behind them. Hopefully this helped.